So welcome to this webinar on MapReduce design patterns. And what we'll cover in this webinar is top 3 design patterns in MapReduce. And before I get started, let me just give you a little bit of a background about myself. So my name is Anupam, and I currently run a startup in the field of big data and text analytics. And we're actually doing a product for the travel industry at the moment. And before this, I have experience across scalable and distributed systems. And I have worked with Sun Microsystems before this for almost 11 years. And I have almost 18 years of experience in this industry. Okay, so with that, let's get started. So what we're going to be covering today is we'll talk about 3 different design patterns, which is about MapReduce. We'll talk about summarization patterns, we'll talk about filter patterns, and we'll talk about join patterns. And we'll have a look at one example from each of these patterns. So when we talk about the summarization patterns, we'll have a look at numerical summarization. When talking about the filtering patterns, we'll talk about finding the top K records. And we'll talk about join patterns. We'll have a look at the reduced side joins. Okay, before I get into talking about the patterns itself, because all these patterns use the constructs which is given by the MapReduce. So what we'll do is we'll quickly have a look at why actually we need to have an understanding about the MapReduce design patterns itself. So so to broach the subject, let's have a look at this question. So suppose you are asked to solve a problem like sorting. And if I ask you to solve a problem like sorting using one of the traditional algorithms, which is either quicksort or merge sort, will you be able to use the same algorithms and solve your problems on a MapReduce framework? Well, of course, it's not possible to do it that way. And why it's not possible? So let's see how a quicksort algorithm, for example, would work. So what you will do is you have this a big set of data, and the way quicksort actually works is you make subset of that by dividing those big set that you have into subsets, and you keep on dividing those till you reach the least unit of that, and then you start combining them together back, and then same way you actually recurse back, and you have the whole thing sorted out. Now, one thing running common across this, if you follow this properly, is that you need to have a look at the full data at any single point of time to be able to do this merge. So your process needs to have a full view of the data. But see what happens in MapReduce design patterns. The framework is imposing certain constraints to you. And what are those constraints? So one of the constraints is that if you have 5 mappers running in your MapReduce job, then none of these mappers will be able to talk to each other, because the only point at which these sort of a synchronization that happens in your MapReduce framework is at the time of the shuffle and sort. Apart from that, each of these mappers generally run independent of each other, and as far as reducers are concerned, they will run after the mappers have finished execution. So in terms of being able to communicate across this, there's no way for them to communicate. So if you have a big data set which has been divided into multiple splits and given to different mappers, to be able to implement your quicksort in similar fashion on the setup is not going to be easy for you, because these mappers will not be able to talk to each other. So because the framework is imposing certain restrictions, the programmers don't have a full control over the way they would have had, they would actually have liked to have. But then, of course, because this is a powerful framework for you to execute and run your programs, so at the same time, although it's imposing certain constraints, because it's following in some ways following the functional paradigm of programming, it's also giving you certain facilities to make you to be unable to execute your programs, write your programs in certain ways, so that you are able to perform your jobs in a fashion uh, which is in conformance to the way MapReduce framework would work. This slide here again talks about some of the constraints, and continuing with talking about some of those constraints. Basically, you don't have any control as to where your mappers or reducers would run. You don't have any control in terms of when a mapper or the reducer begins or finishes. Generally, you don't have too much of a control in terms of which input key value pairs are processed by a specific mapper, and which intermediate key value pairs are processed by a specific reducer. So the idea behind listing these things down over here is, if you had some of these controls, you probably could have used some other constructs of the programming to be able to make some of these mappers or reducers talk to each other and maybe achieve some purpose that within the constraints of the framework itself, on a vanilla framework itself, is not possible. Okay, so that brings us to the question of why we require the MapReduce. So we posed certain questions in the last few slides that we talked about. So the answer to this is, to be able to program efficiently on MapReduce framework, you need to understand the certain ways of writing your programs, and that's where the patterns actually come into picture. And because these patterns have been perfected over the years by experts who have made sure that this is the best way to write and achieve certain objectives of programming. It's best to understand some of those patterns, and you will generally tend to encounter these patterns when you are writing the programs in your daily work, when you are writing programs for MapReduce framework. The scenarios would be different, but once you have these patterns in your mind, it will occur to you that probably this is a pattern which can be used when you're programming in some parts of the MapReduce. All right, so you can have your questions coming in, and at different you can have your questions coming in at different points of time in this lecture. I will go ahead and answer some of those questions. I see a comment that you're not able to see any slide. No, let me see. Well, from my side, when I see here, it shows that the slides from my side are actually shared. Okay, so now you're able to see it. Okay, thanks. All right. So let's move on to talking about the first pattern for today, and that's a summarization pattern. And before I get into this, let me give you a slight idea as to variety of patterns which are generally accepted in MapReduce at the moment. So you have the summarization patterns, you have the filtering patterns, you have data summarization patterns, you have join patterns, you have certain meta patterns, you have graph patterns, you have input-output patterns, and there are other varieties of those as well. But generally, this is the sort of category under which most of these patterns will tend to fall in. Okay, so let's talk about the summarization pattern. Generally, among the most easiest patterns that you would see, and what summarization patterns actually do is, when you're dealing with a huge data set, what you do is, first of all, you go ahead and create a summary of that data. And that's useful from the perspective of being able to get a high-level view of the data, so that once you have that high-level view of the data, you can go ahead and double-click on certain parts of the data and do further deeper analytics in some of those. And that's where the use of summarization patterns comes into picture. The summarization can be in different ways. So one of the ways of doing summarization will be based on your numerical data. The other could be on your text data as well. So some of the summarization patterns which deal with text numerical data is to do with calculating some of the statistic on your data. So that could be calculating the mean, median, mode, variance, those kind of things in your data. And the other thing could be creating indexes on your data if you're talking about the text data. And it's useful from the perspective, as I said, from having a higher level view of understanding of your data. Okay, so I'm going to give you an example of the numerical summarization today. And what you have to keep in mind is, in terms of the actual operations which is performed by summarization, especially when talking about numerical summarization, the operations which is performed inside this are not very complex. The operations is performed is basically you're summing your data, you're counting, you're calculating some kind of an average, variance, those kind of things are being done. But what you should keep in mind when I'm talking about these patterns is the main takeaway probably would be the use of the way combiners are used in some of these patterns. So for example, if you are using a combiner in numerical summarization, we're doing the sum. There, the use of the combiners is really effective because the amount of data which you will end up transferring across the network to the reducer side, or the amount of disk IO that it will do, will end up reducing if you're using combiners. Here is a structure of the numerical summarization. So as you can see in this diagram here, you have these different mappers here, and these mappers are dealing with their own input splits. And the output from each of these mappers is the key on which this the grouping is going to be done. And then you have this summary field over there. On this slide, although the combiners are not mentioned, but generally when you're dealing with numerical summarization, it makes a lot of sense for you to be using the combiners, because that will reduce the amount of data which gets transferred across the network here. So then you have these partitioners, and these are generally by default, these are hash partitioners, but depending on the skew in the data, you could go ahead and use one of your custom partitioners as well. So if you know that there definitely is a skew in the data, then definitely it makes sense to go ahead and use a custom partitioner over here. And then all these things based on the key would be grouped on these reducers. And then the actual function of doing the summarization will be performed inside these reducers. So for example, if you're summing the data, it's going to be the reducer should perform that function. One of the things which, apart from the combiner, which you definitely need to consider here is the associative and the commutative nature of the operation that you're performing in the reducer. Now, if the operation that you're performing, for example, if you're summing or if you're calculating the minimum or calculating the maximum, then in those scenarios, because these operations are associative and commutative, you could go ahead and use the same reducer code that you have as the combiner code as well. So you need not go ahead and write separate code for the reducers and the combiner, which will not be the case if your operation is not associative or not commutative. And that actually happens. For example, summation is one of the numerical operations which is associative and commutative. But if you look at averaging, that is not associative and commutative. So in those scenarios, you would not be able to use your reducer code directly as the combiner code. You will have to make certain modifications to that effect to be able to achieve that purpose. Okay, so the stuff on this slide, I guess when I was on the previous slide, I have spoken about these. So I'll go ahead and skip the slide. Okay. So how does numerical summarization do in terms of the performance? And if you remember, we have talked a few things already. So we have talked about the combiners. We have talked about custom partitioners. And if you look at it from one perspective, the very core function of the MapReduce framework is to be able to uh, group based on the keys. So at a single reducer, everything with the same key will arrive at a single reducer. Okay, so if you have uh, different key value pairs being emitted by different mappers where the value is x, all those x's would actually line up at the same reducer. So that is the basic functionality where the grouping based on a certain key is done by the framework itself. And that helps in the summarization. So because uh, when you're doing summarization, you actually do summarizing based on a certain group. So if you're summing, for example, you will be summing based on a certain key. So that key probably happened to be x, and there were multiple values to that, and then at reducer is summed all those values. But that sum was a correct operation to do, because all the values with respect to those x key value happen to be at the same reducer. Okay, and that's a functionality which is done by the framework itself. You don't have to write any further program for that purpose. These are some of the use cases of numerical summarization, and we did touch upon some of these earlier. So min, max, and the count. So a lot of analytics has to do with doing min, max, and count, and performing some of the min, max operations on your data, if you're talking about numerical data. So numerical summarization is definitely a useful pattern in those cases. And then the word count example, and this is from more from the text analytics perspective. And this is also sort of a hello world of MapReduce, because whenever people talk about MapReduce, is the first example they tend to give. That's word count. But that's also in some way numerical summarization, because summarizing based on a certain keyword. And you're trying to figure out in where all in which documents that certain keyword tends to happen. There's another thing which you should keep in mind, and that's more in terms of the data flow, is when you're using your combiner, you should not depend on the combiners for the correctness of your program. So a lot of times what can happen is even if you're provided a combiner, the combiner might be run by your MapReduce framework, or it might not be run at all, or it might be run more than a single time. So in terms of the correctness of your program, you should not depend on the combiner. So for example, the example which is showing on this slide over here. So the users 1, 2, 3, 4, and 5. The 3 different records for that, and this is the min, max, the count values for them. So the combiner, once the output had come from the mappers, the combiner worked on that, and when the reducer got its input, this stuff was combined. So 1, 2, 3, 4, 5, those users were combined together, and the min, max, and the count was already calculated for them when it reached the input for the reducer. And similarly, the same case for 5, 4, 3, 2, 1. They were also combined together. But if you see the last 2 records here, which end in which are 5 9s over there. So these were not combined by the combined by the framework. So you see these 2 values going as it is to the reducer. Okay, so I'll show you an example of the min, max, count. Let's give me a second here. I'll just open this code. I'll do a code walkthrough for that. So what we're actually going to be doing in this example is we are having a look at the Stack Overflow data. So Stack Overflow data has multiple tables in it, and we are looking at, if you have some idea about the Stack Overflow data, so there are posts over there, there are comments over there, and posts could be of different types. Posts can be a question over there, it can be an answer over there, and there can be comments file, and there are multiple other tables in there. So for example, one of the tables is badges table, and badges table has different kinds of records in it. Now in this example that we are having a look at it is what we're going to do is each of the records in the badges table has got fields. So one of those fields is the creation time of that, then the last updated time of that, last updated date for that badge. And then what we're trying to do here is we are trying to count for each badge types. We are trying to figure out the min, max, and the count for that. So let me go into the code for that. Okay, so here we are. Let me go to quickly go to the driver code for this. So here is a class min-max count, and we are providing an input location, which is badges.xml file, which is coming from Stack Overflow. And then this is your output location. Some of this stuff is boilerplate if you have some experience with MapReduce. So I will skip those parts to this. And here we are setting the mapper class. We are setting the reducer class here. And we are also using the same reducer class as the combiner over here. Remember, I told you, because this is an associative operation, min, max, and the count is an associative and commutative operation. So it's possible for us to use the reducer as the combiner as well. And then we are setting the output key class and the value classes here. And again, this is setting the input and the output directories. So that's the driver code. Before I get into showing you the mapper code, all this, the code itself is quite simple. You should understand more in terms of where you should be using the combiner, what is the purpose of using summarization, and those kind of things you should be understanding. So for example, if you're looking at the min-max count, so we have a class over here, min-max count tuple here, which is maintaining this min-max and the count dates, and then the get setter and the getter methods. And because this implements are writable, so we have the read fields and the write methods, which is overridden. Let's go to the mapper code here. So this is the utility which is reading from that XML file. It's reading one record in each of the calls to this map. It's reading, it's making one call to badges.xml, reading one record over there, and then it's getting passed, and all the fields in that record is being put inside its parsed map. So one of the fields over there is this date, and that's what you're getting, and this name is the name of the badge. So these two fields we have got. And remember, our idea was to group things based on the badge names. So this name will actually become the key when we go down there. So when we are writing to the context here, we're using this badge name as the key. And we are creating a tuple, which was a min-max count tuple. And the values which we are setting in that is this. So we are setting the same value for the min and the max. And we are setting the count as 1. Looking at the reducer code, so at this reduce, based on each of those badge names that you have, so if a badge name was X, so all the values with respect to that X would line up over here. And then basically inside this for loop, what you're trying to do is, you first of all, you're maintaining a running sum of the total counts of the records that you have seen with that badge name. And then we are setting the min and the max values in this part of the code. And then that stuff is getting written out, and that's what you'll see in your HDFS file that is writing. Okay, so with that, let me quickly do a run for this. Let me show you a run for this. And just give me a second. I'm just doing a setup here. Give me a minute here. I'm having some issues connecting with my remote server here. So I'll continue with the slides and I'll explain to you the demos for this. In the meantime, I'll try to get the stuff working. Okay, so we have seen an example of the summarization patterns, and we had a code walkthrough for this. Then we'll move on to talking about the filtering pattern. And basically, filtering pattern, as the name suggests, is about filtering a subset of the data which is of interest to you. And what you should keep in mind is there's a difference between filtering and summarization pattern, and that's more with respect to the data in summarization patterns tended to change because you're either calculating some kind of a statistic or calculating some kind of an index over there. In filtering pattern, although you're looking at data which is of interest to you, the difference is that you're not changing the data that you're looking at. Okay, so basically based on a certain condition, you end up picking up certain records which are of interest to you, and that's what we actually filter in. The rest of the things are filtered out. That's the main fundamentals behind filtering pattern, but there are different varieties of filtering patterns, and they are very useful for purposes of analytics on the big data. I'll give you an example of a simple example of top 10 today. At some point of time, in one of my earlier webinars, I have discussed about Bloom filters, which is quite useful for people who actually deal with big data. And then there's another type of pattern which is again filtering, that is called distinct patterns, distinct filtering pattern. Although by name it actually does not look exactly like a filtering pattern, but in its behavior it's pretty much like a filtering pattern as well. But today we are going to be concentrating on top 10. Top 10, as the name suggests, is about getting the top 10 from your big data set. Now, the stuff that you should keep in mind when we're talking about top 10 is you could solve this problem in a traditional way. And the way you would generally solve this problem in a traditional way is you will first go ahead and sort your data, and then you'll go ahead and pick up your top 10 from that. That's a simple way of doing that. And that's quite efficient if your data set that you're dealing with is not very huge. But if you're dealing with very huge data set, then in those cases, if you're trying to sort your data using MapReduce, sorting, joining, and these kind of operations where most of the data that you have generally tends to get transferred from the map side to the reduce side, the performance of those it's actually resource intensive to be doing that on MapReduce. Although they are very useful operations on MapReduce, but you should keep in mind that they are resource intensive operations on MapReduce. So in cases where you can actually avoid using them, you should go ahead and avoid. And one of the ways which you should be able to avoid is in the scenario where you're talking about top 10 patterns. And we'll show you a different way of figuring out the top 10. Here is the structure for top 10, and you have these 6 different mappers over here, each of these having their own input splits. And the way this algorithm works is each of these top 10s, these mappers are going to emit their own local top 10s. So as you can see here, there's a local top 10 from this mapper, and so on and so forth from each of these. Now, then once these top 10s have been emitted from this, you will need to have only one reducer here. With one reducer, again, you will, in terms of the functions, you will apply the same things which you have done in each of these mappers. What you will do is you get this data sets, and inside this, you will go ahead and create top 10s from all these. And the way you do this is inside each of these code, for example, inside this mapper code here, you would maintain a sorted tree map, which keeps your data in a sorted way. And then you'll keep on inserting the data in this. When the first record comes in, you insert in this tree map. When the second one comes in, you insert. And then when it reaches 10, you have inserted 10 in this. And you're sure that these are the top whatever you have seen, these are the top 10 in that. And then once the mapper receives record number 11, at that point of time, what it will do is uh, uh, it will insert that stuff, but it will after inserting, because once you have inserted that record, you will have 11 records in your tree map, and then it takes out the top one from this one, from that tree map. So once that is taken out, again you're left with the top 10s, and that operation is performed beyond any record that you see beyond number 10, and that same operation happens to be in each of these, and the reducer also will perform the same function over here. And we'll see in the code how this is all performed. And then ultimately, what you will have in that tree map from this reducer is the final top 10. Okay, and this is in terms of the efficiency, this is much better than sorting your whole data set and then taking other top 10 from that. But again, keep in mind one more thing. Now, we are talking about the local top 10s here. Now, if your data set is very huge, and the proportion of the data that you output from these mappers is also very huge. So maybe instead of top 10, if you had just take for a simple example here, this mapper was handling 100 records, and then instead of top 10, what you're emitting was top 50 or top 60 from each of these locally. Then it does not make sense to do this, because look at this reducer over here. This reducer is a single reducer, so it will get all those records, and chances are high that if you are emitting high number of top n's from each of these mappers, chances are high that your reducer here will run out of memory. So to avoid this, make sure that you use this pattern only in scenarios where the n that you're emitting out from these ultimately as a final output, that n is small in terms of the proportions. And again, on this slide, I guess I'm explaining things which were described on this previous slide. And one thing which you should keep in mind is you will not be using any of the combiner and the custom partitioner here, because each of these mappers are emitting top 10s, and all those top 10 records need to be transferred to the reducer side. So there's no sense of using combiner and custom partitioners over here. So the use cases for this would be doing some sort of outlier analysis on your data. So the outliers could be either top 10s or bottom 10s. So that gives us a picture. And probably when you are preparing some interesting dashboards, you're doing your analytics, then you want to show these kind of results out to the end user. So in those cases, you will go ahead and use this pattern. Let me do a code walkthrough for this for you. All right, so here we are. And let me again go to the driver code, because that seems like a good place to get started. Again, so the inputs that is going to take is this input location, and so whatever is the record. So this what we're going to do is we have another table in Stack Overflow that's called users.xml, in which the records for all the users are maintained, and then each of those records have got one field which is known by views. So what we're trying to do is we're trying to figure out the top 10 users by views by this program. Okay, so here we are setting the mapper class. We're setting the reducer class here. Setting the number of reduced tasks to 1, and this is important because if you don't do this, then you will have a partition set of local top 10s coming out of the reducers. It's because you want the global top 10, so in this case it makes sense to use a single reducer. And remember, as I told you, that n doesn't have to be too high here. All right, and as far as the output key class is concerned, that is being set to null writable, because we're not interested in the key itself. But as far as the value is being written out, we are writing out the whole record as the value. So that is being set as text.class. Okay, so now let's quickly go and have a look at the mapper. As told you, this is the tree mapper over here, and this map is going to be called for each of the records which is read from user.xml data. And again, this is a utility to convert the data from an XML record into a map which contains the key value pairs for the fields. Okay, so you have the user ID here, and you have the views, and that's what we'll output from. Let me state this code rather than coming to the end here. So what we're doing is this is a top 10 map, this is a tree map, and we are inserting these values in it. Okay, and then this is the place where we are checking whether the number of records has gone beyond 10. If the size is greater than 10, then we remove the first key from that, and the first key is the smallest key in that. So you would have kept the top 10s in that list that you have of 10 records in there. So once that is done in the cleanup, once the map task is going to get finished, before it gets killed, this cleanup is going to be called, and then you read all these values from that and write those records to HDFS from here. All right. Yeah, so that was the code walkthrough for the top 10. Let's move ahead and let's see examples of the join pattern now. Keep your questions coming in. Maybe at the end, I will answer some of those questions for you. Okay, so the purpose of the join pattern is that your data that you have in your system exists in silos. So some part of the data could be in one system, then you have some part of the data in other systems. And it might not even be completely within your intranet. It could be something completely external to your company's boundaries. So for example, if you're talking about CRM data, for example, right? So CRM marketing maintains a CRM data about its customers. And then there's another set of data which is on Twitter. Now, to enrich your CRM data, what you're trying to do is you're trying to link the data with the Twitter account of that person and get all those data and join them together. And that once you combine this data together, the quality of the analytics which will come out of such data will definitely be much higher, because what you have added by adding such data is, in this case, we added more behavioral information from the Twitter data. So definitely there's a lot of use cases and utility for using the join patterns. And join doesn't happen here only. In the traditional RDBMS systems also, you have varieties of joins happening. But when you're dealing with big data system, at times it makes sense to do these joins upfront before you're performing operations on that data set, rather than doing that on the fly that you generally do in the RDBMS data set when you combine those things on the foreign keys. Before I get into talking about the join pattern, we'll have one example of join pattern today. Let me just quickly give you a refresher on different varieties of joins that we have, because ultimately join patterns will perform one of these joins. So the inner join is about if you have two different tables, table A and table B, and you are trying to combine these two tables together based on some kind of a key value. Okay, so it could be a foreign key in a traditional RDBMS system. In Hadoop, it could be one of the fields in your data. Okay, and so when you're doing an inner join, only the fields where there's a match based on those fields, those records are combined together. The rest of the things are left aside. Other variety of join is outer join, and there are different types of outer joins. So there one type is left outer join. So what happens in left outer join is you have a table on the left hand side, you have a table on the right hand side, table A and table B, and what you do is you of course combine the data from table A into table B where there are matches in terms of certain fields. So that's similar to the inner join case, but beyond that you do certain other things as well. So for example, uh, if you have certain fields in the left tables, for example, in our case, it's table A. So there are certain fields for which certain records, for which there were no matches with records in table B. Those records are also picked up when you're doing a left outer join. When you're doing a right outer join, it's sort of a mirror replica of the first one. And what happens in the right outer join is basically table B, which is on the right hand side, you pick up all the records for which there are matches in terms of the foreign key, and then if there were other records in table B for which there were no matches in table A, you pick up even those records in the right outer join. And what happens in full outer join is it's actually a combination of the inner join, left outer join, and right outer join all joined together, and modular the things which have come in from all these joining together. And anti-join is about, as the name signifies, join by its very name has the connotations of inner join. So anti-join is anti of inner join. So what happens in that is you have the full outer join. So from that you will remove things which are inner joins, and the rest of the things are kept, and that forms what is the anti-join. And then you have the Cartesian product, which is more like a cross product of m cross n. And generally, this is something which is very resource intensive to do. So you're advised to avoid these if you can do. But there are certain scenarios when you're doing your analytics. For example, if you're trying to do similarity analysis across multiple documents, maybe thousands of documents, then in that cases, and you probably would have to go ahead and use some of this Cartesian product to be able to understand this similarity analysis. Okay, so the example that we're going to be using for the join pattern today is the reduce side join. And let me just quickly talk about a few lines on the joins which happen on the reduce side and joins which happen on the map side. So there's certain joins which happen. So when you're talking about reduce side join, these are much more easier to implement, but the most costliest of the operations that you will perform on the framework, because in reduce side join, all your data is going to be transferred from the map side to the reduce side, and the whole operation of joining will happen on the reduce side. There are some varieties, different varieties of reduce side join, and then there's another type of joins which happen completely on the map side. So something called the replicated join that happen completely on the map side, but when you move, and they're much more efficient to do because you're not transferring your data from the map side to reduce side, but you're getting certain benefits by doing this. That is, you're not, in terms of the efficiency, you have increased the performance of your programs. But there are certain things which you're losing when you are moving completely from the reduce side to completely on the map side. And that is in terms of the flexibility and the kind of operations you will be able to perform. So there are certain types of joins which you will not be able to do when you are moving completely to the map side. So if I'm talking about replicated join, whereas on reduce side join, you could have performed all the join types that I have talked about on the previous slide. When we are doing things completely on the map side, you would not be able to perform the only types of join you will perform, especially with the replicated join, is the inner join and the left outer join, not the other ones. All right. So so I was talking on the previous slide. One of the things that I missed talking about was the fact that when you have more than one large data source, so you could join two data sources together, or you could join multiples of those. Maybe you're joining maybe 5 or 6 of those together. Now, if you're doing this and all the data sets that you have is actually large, then you're left with no option than to go to the reduce side join. But if you have some options, for example, if you have one data set which is large and there's another data set which is small, then you should avoid using reduce side join, because replicated join will be able to perform that function quite perfectly and quite efficiently as well. Here is the structure for the reduce side join. So these are two different data sources. Data set A is one source, data set B is another source, and you have three different splits in data source A, and data source B has got two different splits. And then these mappers are getting those splits. And what has to be kept in mind is the key value pairs is going to be emitted by these all these mappers. They have to keep in mind the foreign key on which they're going to be combining these records together on the reduce side. So the key has to be the foreign key based on which these records would be combined. Of course, foreign key is not something which makes sense when you're talking about big data itself, but again, it's a key which is similar on both the sides, which have similar meaning on both the sides. So in this case, here's the name of the person, Bob, which is being emitted by each of these mappers, and they will be combined on the reduce side based on this key. And then these are the values which could, in this case, it's a single field being emitted, but the payload could actually be the whole record as well. But one of the things you can do to improve performance of the reduce side join is you could do a projection in your mappers. So instead of passing the whole record to pass through the shuffle and sort phase to the reducer, you could actually do some projection on your data. So and pass only the fields which are of interest on you in the output, the fields of interest to you. And then in the reducer code, in the join reducer code here, you will see the actual type of join which is performed is actually being done over here as far as reduce side join is concerned. Again, on this slide, I guess, let me see if I missed something when I was talking on that diagram. Okay, I just missed talking about the combiner. So combiner will definitely not provide you any additional benefit here because, as I said, everything needs to transfer to the reduce side. So combiner would not be able to be of much use. You can use custom partitioner if you think your data that you have is skewed. So custom partitioners can be used in such cases. In terms of performance, I've already spoken quite a few times about this on previous slides. All right, now let me go to a code walkthrough for reduce side join. All right, so again, let's have a quickly have a look at the driver code here. So here's reduce side join. This is the class, and then what we're trying to combine here is again, I told you about the post.xml, which is there in Stack Overflow data. There's another field by the name post links location. Let me not go into the details of this, but what we're trying to do is we are trying to join the data from these two together here. And this is a place where we will write the data out ultimately. And you also have to provide what kind of join you want performed on the reduce side here. So you can have one of these options given: inner, left outer, right outer, full outer, anti, because remember, right, the reduce side join is able to perform all varieties of joins. So you can use any of those. All right. So let's see. Now this part of the code is about making sure that you're passing the right type of join to be performed. Let's see. Yeah, this part is interesting here. For doing this join, we are using a class called multiple inputs class, and this is a class which is provided by the framework itself. And what we are going to specify in this multiple inputs is the source from which this input, multiple input, is going to read its data. And also you can specify the mapper which should be working on that input split. So as you can see here, these two multiple inputs have different mappers being given to them. So the first one is for join mapper. This is join.xml. And the second one is for postlinks.xml, which is postlinks join.map. join mapper dot class. And then the path which is being provided is also different. Remember, the first was for posts, the second was for post links. So they will be reading. By doing this, you're making sure that the mappers will be reading from different sources, and when read from different sources, they will also make sure that they are executing the right kind of join operations. Sorry, right kind of mapper code is being executed on them. And then you're setting the reducer class here. And then rest of the things is boilerplate. I'll just leave that. Let's quickly go and see the mapper code here. So okay, so this is for the post mapper, post join mapper, and it's reading this value ID of the post, and that is being set as a key here. And then we are setting the value is being set as a whole record which has been read. So this was the whole record which is getting passed in, and we are setting that as the output value. But along with that, we're also prepending a P to be able to identify where is that value coming from. That's going to be used when we are dealing with this part of the code in the reducers. And then we write this out, this key value. So the ID is here and the whole record is here, prepended with a P because it's coming from posts. Then in the post links, almost similar thing being done here in this part. So we're reading the post ID here, which is sort of similar to the ID in post.xml. And again, we are, as in terms of the value, we are going to be writing the whole record out. But what we are doing is we are prepending a L in front of that to be able to decipher in the reducer from which of the mappers that value was generated. Once that is done, you have the reducer code here. And there's a setup method here in which setting the type of join which has been passed in, because that's being read from the configuration here, because that's the kind of join operation which the reducer will perform here. Before, so the actual join is getting performed inside this method here. It's called execute join logic. But before we do that, we make sure that the values are getting stored in the right lists. So we're maintaining two different lists here, one for the list post, and the other for list post links. And in this for loop, we are filling up those two different lists with the right kind of source records that you can see here. So once that is done, the list post and list post links have been filled up. We call the execute join logic, and that's where the actual join operation will happen. So let's see quickly the code for at least one of these. Here we are trying to perform the inner join operation. Remember, the inner join operation is more about getting an intersection of two different tables. And if one of these tables happens to be empty, then the whole result is going to be empty because there's nothing to combine with. Okay, so that's what we are checking here at the start. So if list is empty, either of these lists is empty, at that time nothing is going to be printed out. So making sure that none of these lists is empty, list post is not empty, and list post links is not empty. If that is the case, then you'll just go ahead and combine these two together. So you have two different loops here, one outer for loop, and there is another inner for loop. And for the outer, we are reading from list posts, and for each of those records which come out of list posts, so we combine them with records coming from list post links, and then we write that data out. Remember, at this point of time, whatever is contained inside list post and list post links, all those records have been matched on certain keys already, because the reducer would have taken care of this. So this key was the matching value, and after this for loop had executed, post links and these two records here, all the records in both of these lists had the same key. So that's the logic for doing the inner join. And similarly, you can see in the code how to do the left outer join, the right outer join. the left outer join. The logic is slightly different for each of those, so you can have a look at that code. We don't have much of a time to go into that. So that's how the reduced side join is performed. There's another variety of reduced side join that's called reduced side join with Bloom filtering. What happens in that is your records to a certain extent are removed on the mapper side itself. So things which is not going to be of interest to you, you know that these things are not of interest to me. So you train a Bloom filter on that first, and then the Bloom filter acts on removing those things right on the mapper side. And then you get things, only the records which you are interested in on the reduced side. So that's a sort of an improvement in terms of performance. But again, as far as the join operation itself is performed, the whole join operation still is performed completely on the reduced side for any of the reduced side join patterns, even the ones with reduced side join with Bloom filtering. All right, so I'm done with the examples that I was supposed to talk about. Let me quickly see if you have some questions which we can go through quickly. Okay, let me see the answer. So initially we have a lot of things related to the late start of the class. Sorry for that. And there's some problems. So there's one question that says, what is design patterns in MapReduce? So I guess by this time that probably would have been answered, because design patterns are patterns which will help you solve the problems in standard ways when you are writing your programs for MapReduce. Rather than probably you would reinvert in your own ways of doing it, but these patterns already have been tested through people having experimented with that code over the years. So they are the standard ways of solving certain kinds of problems. So they are the patterns which you could go ahead and use. Yes, so there was, I guess we have control over which intermediate key value pairs goes to which reducer. Yes, yes, I did not mention it over there because I just wanted to keep it simple. As far as the intermediate key value pair is concerned, yes, you have some control over there with the custom partitioners. What's the advantage of design pattern? I guess I did answer this question now. In emergence of Spark, whether MR has relevance. So rather than talking about MR, I would say Hadoop and Spark. They're two different ways of solving the problems. And these design patterns are specific to the Hadoop MapReduce patterns that I'm talking about. So, but as far as the design patterns itself is concerned, you could use similarly on Spark as well, but then of course the construct that you'll use over there is going to be different. Another question was about skewed dataset means. Skewed dataset, so what I mean by that is you have got 3 different reducers, and you have 100 records to be shared across them, and you end up giving 70 records to one of those reducers, and 30 is distributed across the rest too. Then that's called the skewed dataset, because the time that your MapReduce job is going to take to completion is going to be much more higher than if you had done a distribution which was much more equal across these. Is the session shared? I guess these things are going to be recorded and should be on someplace on Edureka's site. I understand is Java is a must for this course. Okay, so So MapReduce, this is a course about MapReduce design patterns and writing code in Java. But then the codes and the idea from the course is to understand the patterns so that you use these things in your work environment and when you're implementing different other complex systems. Now, I I generally try to keep the Java code itself simple. So if you have some background with understanding one of the object-oriented programming languages, so you should not have too much of a difficulty in terms of understanding the code itself. Can I get the code for these patterns discussed? I guess the code is not on, it's not shared at the moment. What is performance hit, map side join or ready side join? Okay. Uh, so if I have not made it clear so far, so this ready side join was talking about because this whole set of records that need to be transferred across to ready side. So there is definitely a performance hit in terms of the network bandwidth which this is going to take. When you are completely on the map side, so there are certain stages, so shuffle and sort stage, combiner stage, partitioning stage. These things do not have to be brought into picture. So they would not run, and also in terms of network traffic across the whole framework, you do not have to transfer the data. So that's where the benefit of the map side and comes with respect to ready side. So each mappers run in different JVMs. Yes, they do. Do we need to understand the design pattern in MapReduce to do big data analytics? Okay, so big data analytics you can do using Pig as well. It's not completely required to be writing your programs in Java, but there are different varieties of programmers. There are folks who are Java programmers. There are folks who are more from the declarative language part, and Pig is more of a data flow language. So when writing your programs using Java, then definitely these things are required. But then one of the things you should know is whatever you're writing in Pig, everything gets transferred into MapReduce. So when the complexity of a Pig programs tend to increase, it's always good for you to understand how it's done in the Java MapReduce to be able to write better programs in Pig itself, because you will understand the performance aspects of it if you are understanding how the things are going to get translated when it's going to be translated into MapReduce. So from that perspective, it's useful. How much this is important to know when Hive and other frameworks does this for us? I think I just answered this question for you, because a lot of these things will get translated into the Java MapReduce. If I'm performing all my join logic in map side, do I require reducer at all? So I guess I answered this question because when you're doing all your join logic on the map side, there are certain things which you'll have to, in terms of flexibility, you will have to lose. So I said, not all kinds of joins can be performed completely on the map side. And also, there will be restrictions in terms of how many large sources of data you will be able to use on the map side. Does MapReduce design pattern same across all versions of Hadoop and all Hadoop distributions? Yes, it will work across all of these because there's actually a Java code. The client. Okay, so how to choose can't we use partitioners for join? Yes, you can use the partitioners for join. Yeah, so as I said, whenever there is skew in the data, you can go ahead and write. Partitioners are used. I mean, the default partitioners anyway are used. That's a hash partitioner. But if you're seeing a skew in the data, it makes sense to write custom partitioners as well. How to choose among so many patterns? Well, this is something which will form in your mind, and slowly over time, you will understand that you can go ahead and use. This will come. So there is a course on this, which is MapReduce design patterns, which I generally do every month on Edureka. And So the question is how to choose among so many patterns. So these patterns are meant for different purposes. And as you get more understanding about these patterns, these tend to form in your mind. And when you are working in your own environment, on your development environments, you will come across problems where you will think that you had learned about that pattern that probably applies over here. So that's something which comes with a little bit of practice and understanding, and that's the way to do it. Uh, and then of course, maybe your question had some other connotations as well. So for example, I'll just because we talked about join patterns, let's talk about the reduce side join and the map side join. So you could use any of these patterns for solving your problems, either the reduce side join or the map side join. But uh, the benefit is depending on the kind of data sources that you have, depending on the kind of join operations that you have, you will have to take decisions. So that's where such ingenuity will come into picture. Whether different mappers could communicate between each other? No, it's not possible for mappers to communicate with each other. The framework does not allow you to do that. So each mappers would work on their own. They will write the key value pairs, and it's actually the shuffle and the reduce phase that the mappers themselves don't talk to each other, but actually the data from these things come together in some ways. All right, any more questions? Okay, so if nothing else, I'll call it a wrap. Okay, there's one more. And client driver class also runs a different JVM from the mapper and the reducer. Yes, it runs in a different JVM. Okay, thanks. And if no more questions, we'll call it a wrap. Okay, thank you. It was nice interacting with you guys, and see you later. Okay, thank you. Bye.